just a little bit of my background. I'm a product of the East Tennessee public school system. So my English may not shine all the time, but I had a remarkably good science background and a Latin teacher that just taught me logic. And so anything that I do in life, I trace back to my high school when I learned about logic through languages and through science. So I certainly admire all you folks being here and you know, getting more information about what you want to pass on to your students as well. It makes a huge difference. As a college teacher, you probably get this, but just about every year I get at least 4 or 5 students come up to me out of a class of 400 and say that they've changed the way they thought about issues like climate change, or they changed their major, or they've fundamentally changed their thinking. We all come from backgrounds where parents and aunts and uncles have a lot of influence on our thinking, and issues like climate change are very generational, as you know. You'll have your students are probably plugged in quite well, and their parents are probably not. And it's just something we have to live with. It's one of these wonderful sociological issues that I wish we would study more, but we don't. So I went through my educational experience at a time when interdisciplinary anything really didn't happen. And if you're going to study climate, interdisciplinary is important. And so I didn't have the benefit of a lot of good educational structure by me. I sort of had to go hunting for courses and things like that. So I was a chemistry major and then ended up focusing on how the planet functions rather than how laboratories function, although I was trained a lot in how laboratories function and how molecules function. So I was quite interested to come in and hear the conversation about methane and CO2 and vibrational frequencies and stuff like that, because I was forced to take I don't know how many inorganic chemistry classes and nuclear physics and all that other stuff. Anyway, what I want to talk to you about today is very interdisciplinary. And I think that's important because putting it together, putting the pieces together, starting from simple physics and going all the way to how do we view this as human beings is really critical. If you look at climate change on the planet, climate change happens all the time. Climate variability that we see today is no greater than it has been in the past. As a matter of fact, if you look in the past, you see some really remarkable climate changes that human beings had nothing to do with. Yet the physics that drives those climate changes is the same as the physics that drives the climate change today. And that's a message that I think gets lost frequently in terms of how we teach about climate change. And so I'm going to start with some basics on physics and then move into a couple of examples. I don't have a whole lot of time to get into a bunch of examples, but we can do as much Q&A as you want to do. So I'm going to rely on 2 things. I'm going to rely on what we call paleo-environment, paleoclimate, and also simple physics. This is a very powerful combination. Simple physics is simple physics. You simply can't get around physics. You know, once you understand how something functions, then there's a great deal of predictability in there, and we all teach simple physics. And as we'll see, simple physics has a lot to say about the issue of climate change, and I'm sure you all know that, and you've probably been looking at that all this morning. Another very powerful thing that we do is we look into the past. What the past allows us to do is to compare things like how much greenhouse gas was in the atmosphere, how much temperature change there was, and not more importantly, but actually very importantly, what happens to the planet when climates change. Because one of the things that we struggle with as human beings is trying to think about what are the implications of climate change, what are the implications of environmental change, what's going to happen. As it turns out, there's quite a few things that go hand in hand. There's some very predictable positive feedbacks, for example, the amount of carbon in the Arctic, sea level, temperature, precipitation patterns, relatively well predictable things that we can say, yes, this is going to happen if you have a warmer planet, and you're going to have a warmer planet because you put more greenhouse gas in the atmosphere. So we're going in a direction. And so I'm going to talk a little bit about that later in the talk. What I do mostly is ice cores. I'm the director of an institute that looks not only at ice cores. I have to give a shout out to my good buddies who do ocean sediment work, paleolimnology, looking at lake sediments, looking at bogs. I've done some work in bogs. Bogs are really interesting places. Any place where sediments collect. And ice cores are basically a sediment. It happens to be precipitation that makes ice, but they're all kind of sedimentary collections. Ice is interesting and different in that it is very inert. It's just basically H2O, some of the purest water on the planet up in the top of Greenland and Antarctica. And consequently, the air that's trapped in there doesn't get messed with very much at all. So we can measure things like CO2 and methane and nitrous oxide, the greenhouse gases. And I'll show you some of those records. But because ice is so inert, because it doesn't have chemical reactants within it to a large degree, we get some very good records of the atmosphere. And that's unusual. We don't get atmospheric records from some of these other places. So, begin with the basics. And I think you've been talking about this morning, but when I give a public talk, this is where I begin. Global climate depends on 3 factors. And that's remarkably simple when you think about it. And you've talked about this morning, I think. How much energy do we get from the sun? How much of that energy is reflected back to outer space? And the amount of greenhouse gas in the atmosphere. So you've talked about the mechanism. It's really the Earth's radiation we're concerned about. And so in terms of greenhouse gases, and so if the sun's energy is coming in, if you had lots of clouds, if you had a very reflective atmosphere, you would get less energy absorbed at the surface, and so less opportunity for greenhouse gas to do their thing. So all these things interact. How much energy we get from the sun varies. How much of the energy is reflected back to outer space can vary, and the amount of greenhouse gas in the atmosphere can vary. All these 3 things can vary. As a matter of fact, there's some feedbacks between them that we'll talk about as we go along, except for the feedback on the sun. So how do these things vary? Mark asked me to mention probably again, you probably hear this over and over and over again, that the orbit of the Earth around the sun is not constant, that indeed if you go back 20,000 years ago, there was less radiation. Actually, we're pretty much at a low point right now. We ought to be, from a radiation standpoint, well on our way to an ice age. And there's some wonderful debates in the scientific community about why that's not the case. And wonderful meaning that some of them have interesting side issues, such as, for example, did we begin to increase methane and CO2 in the atmosphere, which we began to do in the neighborhood of 5,000 to 6,000 years ago? Did we do that enough to actually stall or forestall the next ice age? And that's a very interesting discussion that, if you really want to get into it, your students can have, a very rich discussion about just when did human influence on climate begin, and have we inadvertently created a planet that allowed our societies to grow and blossom? Because I think it's pretty doubtful that the kind of human societies we have today could have come about had an ice age begun 2,000 or 3,000, 4,000 years ago. We'd be very different shape than we're in right now. Anyway, the sun itself also varies. The sun has been getting hotter as time goes by. Mark and I were just talking about some of the wonderful paradoxes in paleoclimate, one of which is when the sun was weaker in the past, how did we actually have a warm enough planet to have liquid water and therefore all the life we've had for billions of years? And there's another rich discussion right there. But anyway, what we're talking about mostly over the last million to 60 million years has more to do with the orbit of the Earth around the sun. The reflectivity of the planet varies primarily through reflective surfaces. Do you have more snow and ice? And therefore, do you have more reflectivity? And this is very strong positive feedback. And by strong, it's remarkably strong. As an example, the last time that the Earth was warm enough to start to melt out the snow and ice in the Arctic region, Arctic temperatures rose by about 20 degrees Celsius. I'll say that again because it's big. So there were trees, pine trees, growing up to the edge of the Arctic Circle. They're still there because it cooled off fast enough that a lot of those deposits are still available, and you can go in and mine trees that are in the neighborhood of 3 to 5 million years old, and some deposits that are tens of millions of years old. So the reflective surfaces are very, very important, and this is one of the more fascinating little tidbits for you is that the last time the atmosphere had as much CO2 in it as today, the polar regions were melted out. There was not Arctic sea ice, there was not a lot of Arctic land ice, and temperatures were about 20 degrees Celsius warmer in Arctic regions than they are today. Same amount of sun, same amount of everything else. If you just look at the last time you had that much CO2 and methane in the atmosphere, the climate was fundamentally different than it is today. And there's some real questions about whether or not that's the place we're going to go eventually. The other reflective surface is that we know about is volcanoes. And volcanoes have a very predictable impact on climate. When a volcano goes off, there's a certain amount of reflective sulfate that's put up into the stratosphere. Sulfur dioxide gloms onto water. It loves water because it makes sulfuric acid. And that makes tiny little ice crystals up in the stratosphere. And if you come from an area of snow, you'll know that after particularly a dry snowfall, you look out and the surface of the snow just glitters. And that's the sun reflecting off those platelets. And the same thing happens up in the stratosphere. The sun reflects off the platelets. And so volcanoes are a known cooler of the planet, very quantifiable. Yeah, I don't know where I'm going to get through these slides. The amount of greenhouse gas. In the amount of greenhouse gas, biogeochemistry is a brand new word. It's a brand new field. But this is very important to understand that on very long time scales, plate tectonics control the amount of carbon dioxide in the atmosphere. It has to do with weathering. Has to do with the amount of carbon that's stored as carbonate in the ocean, how rapidly are the plates moving together, and volcanoes releasing CO2. Volcanoes are small releasers of CO2, but over hundreds of millions of years, they're an important factor. On the timescales that we're most interested in, ocean circulation is the biggest player in terms of the amount of carbon in the atmosphere. Most of the free carbon in the world on the surface is in the ocean, dissolved as bicarbonate. So when the ocean circulation changes, it changes the atmosphere. The atmosphere doesn't tell the ocean what to do. It's the other way around. An easy way to understand this is that if I were just to plunk over dead right here and begin to rot away, if you guys just sort of callously left me here for the next 10 or 15 weeks or so to begin to rot, my carbon dioxide is going to go into the atmosphere. If you're a fish and you die, that doesn't happen. If you're a fish and you die, you go down, all right, into the bottom of the ocean. Now imagine an ocean that never circulated. It was very stratified. All that carbon, and not just the fish, but the phytoplankton and everything else, is going to fall down to the bottom of the ocean. The bottom of the ocean becomes very rich in carbon. The atmosphere becomes very depleted in carbon because there's this one-way mechanism to take photosynthesis, CO2 out of the atmosphere, make plants, make fish, make everything else. They die, they go to the bottom of the ocean. So it's the vigor with which the ocean circulates from the bottom of the ocean to the top that sets the amount of CO2 in the atmosphere. If you've got slow, sluggish circulation or stratified circulation, you will end up with much lower CO2 levels in the atmosphere. If you have a vigorous circulation like we have today, relatively vigorous, then you blow more CO2 in the atmosphere because you take this carbon-rich water, you expose it to the atmosphere, and it exhales CO2 to the atmosphere. So the ocean drives the bus, if you will, when it comes to carbon. Sir? Bob. So the question is about whether the times when carbon was rapidly accumulated into coal, oil, and natural gas, etc. That was actually a time when the planet was warmer. There was more CO2 in the atmosphere. So plant growth was very vigorous. And the ocean was probably a very vigorous ocean as well. It pumped CO2, it kept atmospheric CO2 levels up in the neighborhood of probably 1,000, 2,000 parts per million. That allowed plants to grow like gangbusters and therefore accumulate large stocks of carbon, which then accumulated as coal, oil, and natural gas that we utilize today. We haven't seen CO2 levels in the atmosphere at thousands of ppm since probably 40, 50, 60 million years ago. Although, we're going there. We got the chops to do it. The other thing that's important that plants, plants cycle carbon, but they cycle smaller amounts of carbon and it's more rapid. So plants are like this buzzing noise on the carbon cycle. The ocean's like this, I can do this. And as it turns out, humans, we don't change much in the way of albedo, although we do put enough gunk up in the atmosphere, both positive gunk in terms of its reflectivity and negative gunk like black carbon in terms of its absorptivity, that we begin to impact the albedo. And there's a lot of debate in the climate community about how much albedo impact we have. But we very clearly have an impact on the amount of greenhouse gas in the atmosphere. So changes in any of these things can cause a climate change. Change the amount of sun, you can cool off the planet. Cool off the planet, you're cool. If you increase albedo for whatever reason, you cool the planet off. You increase the amount of CO2 in the atmosphere, you can warm the planet up. They're independent in that sense, but they also feed back on each other, and you can sort of see those feedbacks, at least in terms of albedo, the feedback's pretty clear. Yes?
Yeah, you said there actually is a lot of debate about how much albedo we're putting in the climate community. Can you elaborate on that a little bit?
Well, there's records of the albedo impact of humans are not very well collected, and people haven't looked at them as seriously as they probably should. But there have been a couple of moments in history when we've been allowed to get a glimpse of what we do. 9/11 was a classic example and a good teaching example of there were no contrails up in the stratosphere. What happened to the climate? You know, suddenly we saw a difference in the amount of radiation making it to the surface of the Earth because there weren't contrails up in the atmosphere. That's a small example, but I think a good one for people to visualize, yeah, the white reflective stuff's not there anymore. It also absorbs as the radiation goes back to outer space. But there's a lot of debate about, for example, our impact on fires. We burn. We love to burn. And that makes soot, black carbon, which can be very reflective, or very absorptive in the atmosphere. And we don't really understand all the impacts there, although we think that black carbon can have a very big albedo impact, positive albedo impact, or negative. Depends on which way you're going. So changes in any one of them can cause a change in climate. That's very important. And the past tells us that the sun has caused climate change, that albedo has caused climate change, and that greenhouse gases have caused climate change. And one classic example is if you go back and look in time, you will find times when the amount of greenhouse gas in the atmosphere increases by a large amount in a short period of time. These are times, and they're rare, when we think, for example, that methane stored in ocean sediments might have burped up into the atmosphere, increasing the amount of greenhouse gas in a short period of time. You get a very dependable increase in planetary temperature when that happens. Right? So we know that we can see in the past that if you increase greenhouse gases independent of the sun, this happened because the planet was warming up and some carbon was released from the ocean and went to the atmosphere. But independent of the sun, greenhouse gases can do their thing. Right? The sun can do its thing, and the sun, you know. So this is a question I get all the time. As a matter of fact, we just got dragged into this. It doesn't matter whether CO2 led or lagged temperature 20,000 years ago. If CO2 went up first, then CO2 was a primary driver of the system. If the ocean went up, if the sun started to warm first, that caused a change in ocean circulation, which then caused CO2 to go up. Both the sun and the CO2 are part of that warming. So I hear over and over again that if the sun started a climate change, in other words, if temperature began and then CO2 happened, then there's no way that CO2 can cause climate change. That's the logic there just causes my brain to hurt. But I hear it all the time. Right? I'm sure you hear it all the time as well. But this is one that you just got to, you know, put your thumb on it, squish like a bug, because this is one of those illogical little loops that we got to get people to get out of. So it doesn't really matter. Greenhouse gases are an important part of the Earth's energy budget. For some reason, this little tidbit tends to get lost as well. If you do a simple energy budget of the atmosphere, of the planet that is, and you look at how much energy we get from the sun, that is how far away we are from the sun, we're not close enough to the sun to be a warm enough planet to have liquid water. Our average temperature with just solar radiation is about -18 degrees Celsius. We'd be frozen. And if we're frozen, we would not be a habitable planet, at least for the species like we have. Probably maybe bacteria. Bacteria seem to live everywhere. But definitely too cold for advanced life. The Earth's temperature with greenhouse gases, that is, if you go out and measure thermometers, et cetera, is about +15 degrees Celsius. And a very simple physics exercise can show you that the difference between these two is primarily greenhouse gases. And so we get about 60 degrees Fahrenheit warming because of the greenhouse gases that we have. So without them, we don't have a habitable planet. And then to turn around and say that if you increase greenhouse gas in the atmosphere, it's not going to cause climate change, it's kind of like, you know, if you think about it, like, you know, taking deadly aim at your own toe and pulling the trigger. Because, you know, we need those greenhouse gases. If we were, I'll just go off on a little bit of a tangent here, but one of the things that fascinates me is that, you know, we talk about greenhouse gases as if, and politics and policy as if human beings had anything to do with physics, as if we could actually change them. And so one of the things that I find very instructive when I talk to my students, you may not be able to get away with this in your schools, but we talk about the difference between, say, abortion as an issue or health care as an issue and greenhouse gases and climate change as an issue. And the fundamental difference is that what we do as human beings, from a policy sense, will change whether or not we have abortions and will change whether or not our health care system is one way or the other. We can change the outcome of those through our arguments and through our arm waving and everything else. We can't change climate change, greenhouse gases. I don't care how many people get on the radio or on TV and talk about the fact that climate change is not real. It's going to change, and it will continue to change, and they can't do a damn thing about it because it's, it's just simple physics. And that's an important difference. And yet those issues all get caught up together. We think that by talking about climate change in a policy sense that we can actually affect things. We can affect things in the short term in terms of human reactions to this, but we're not going to affect the outcome. All right. So greenhouse gases, we've caused greenhouse gases to go up. You can measure any of these things. Up in the upper left is carbon dioxide coming out of the glacial period. You see it's rising up there to about 280 parts per million. Now it's about 380 parts per million. You see the impact of human beings much stronger than any short-term impact that we see in the carbon cycle. Methane is even more impressive. That's the bottom left one there. We've tripled methane in the atmosphere. Nitrous oxide's gone up by about 30%. And the rate of the forcing is down here on the right. All of these things are in the IPCC report. And all of them, it's just, I'll show you. The next slide, I think, is even more instructive. You've probably seen this. This is in the bottom is the methane, and in the green is methane, and the red is CO2. What you're looking at there are Milankovitch cycles, the Earth's orbit around the sun, driving the temperature of the planet, driving ocean circulation, driving CO2 in and out of the ocean. But you see the impacts here. I'm going to point. I mean, that's humans, and the green is humans, and there's really no way we can get around that because there's nothing in the last million years that approaches that kind of level of change. Yes?
When you say we can't change climate change,
we can't change the physics. We can change what we do. We can change the amount of greenhouse gas we put in the atmosphere. We can modify our own behavior in terms of our forcing. But we can't change the physics. That's what I'm saying. The outcome is going to be set once we decide what we are going to do. Our arguing will never change that. So, yeah.
So, sorry, just looking, so you said there was, what's the highest that CO2 has been?
On the planet?
Yeah.
Oh, probably in the neighborhood of 3,000, 4,000, 5,000, 6,000 parts per million. So it's not even on this scale. It's somewhere in the fourth floor.
I always see this one.
Yeah.
And I guess I'm not thinking about the fact that it actually has been a lot higher.
Yeah.
Than what it is currently.
Right. And I think there's a couple of really important lessons lurking in here. One of which is, and we'll back up for a second, the magnitude of change. We've raised CO2 by 100 parts per million. That's the variability between glacial and interglacial times. So in 2007, is my best guess, human beings became the largest impact on the carbon cycle in the last million years. We know at least for a million years CO2 has been contained within an envelope. It's also important to recognize that CO2 has been high, CO2 has been low, we had nothing to do about it, life has gone on. I hear this from my students occasionally. Are we going to create an uninhabitable planet? Are we going to wipe life off the surface of the Earth? And the answer is no. I don't, unless we really got serious with nuclear weapons, which we could do, then I don't think we have the capability to do that. We're not going to do it via the carbon cycle. We're not going to do it via climate change. The Earth has seen extremes far greater than the ones that we are imposing right now, both in terms of magnitude and in terms of, potentially in terms of pace of change. Cockroaches. Oh yeah, something's going to survive. No, I think plants will survive. Everything else, not everything else. We've made things extinct, but and we'll talk about that if I can get through more than 5 slides. Have you guys seen this? Yeah. Okay, I'll skip it. So is it surprising that I want to move on a little bit to the bigger picture? Is it surprising human beings are causing climate change? And the answer is no. I mean, not really. And changing the energy budget of the planet is only one of a whole laundry list of things that we have done on the planet in which we exceed the natural capability of the planet to affect change. Examples. We cause 10 times more erosion than all natural processes. So we're out there with our tractors and our lawn, and the big caterpillar gizmos. We move 10 times more dirt than all the rivers and streams on the planet. We make more fertilizer, nitrogen fertilizer, than all of the bacteria on land. And that's pretty impressive because I can't even begin to understand how many bacteria are out there. But we figured out how to take nitrogen from the atmosphere and turn it into nitrate and ammonia about 60, 70 years ago. Nobel Prize was handed out for that little Hummer. And in a matter of, since World War II, when we got serious about making nitrogen fertilizers, we now make more nitrogen fertilizers than all of the bacteria out there. And in a matter of 50 years, we eclipsed one of the most fundamental biogeochemical cycles on the planet, the nitrogen cycle. Without it, you don't have life, because without nitrogen nutrients, you don't have photosynthesis, you don't have life. We make more sulfate than all the ocean phytoplankton in the world. When phytoplankton die, they produce chemicals that produce sulfate to the atmosphere, and we produce more sulfate than by coal burning, and by accident. We don't even intend to do that, than all the phytoplankton in the world. And this is just, 3 or 4 of my favorite, but there's a whole laundry list of these things. And my message, if I can get through it, is climate change is really something we deal with as training wheels for sustainability. Sustainability is the big picture here. Can we create sustainable societies on the planet? And frankly, if we can't deal with the issue of climate change, then it's hard to imagine we'll deal with even larger issues of land use, of water, of food, of all the other things that we have to do to have sustainable societies. Climate change is part of sustainability because climate change sets the baseline about which we have to react. If climate is changing, and energy to do that. Not 50%, 500% more energy. And so 5 times increase in the amount of carbon dioxide going into the atmosphere. If India was to come along with the show, they're about 8 times below Europe on average. And if you want to compare to the US, and we're pretty sloppy, then you got to multiply all that by a factor 2. So it'd be 10 times for China to get to US, and roughly 15 times for India to get to the US. So which creates for me what I call the nasty dilemma. I've yet to find any of my undergraduates who would like to see people enslaved in poverty and not living well. And yet, if they are indeed to move, if the 3 to 5 billion who live on the very low end of the scale were to move towards our end of the scale, this is going to be a huge multiplier in terms of the amount of energy that's required. Just an example of this, I just pulled these statistics off the UN website, or a UN website. This is the amount of energy used around the world. And you can see that for the most part, the North America, Europe, et cetera, we haven't changed that much. We bounced around a little bit. That's most of those curves down there. It's really the yellow dots, which even I can't read. That's Asia and Oceania. That's China and India. They've gone up by a factor of 2 since 1980. And the other is the Middle East, has gone up by a factor of 2. But that's where most of the increase is coming these days. The industrialized world is still pumping out greenhouse gases as best we can, but the big increases are coming from the industrializing world. And again, you would like them to industrialize. By the way, you can see what happens when an economy like Russia blows up. That's really fascinating that, they just collapsed, the amount of energy used per capita. And now they're slowly crawling back into the industrialized world. And this is my favorite picture. It's kind of washed out. But I have my undergraduates take this, put it on the wall across from the toilet, I tell them that, and say, look at it, hopefully every day. And it's impossible, I think, to stare at that over and over again and not get the message I just given you in words. To me, this visual is just so strong. If you were coming in from outer space, if you were Zork from, Beeblebrox, you came in, you know somebody's big on this planet. You know something's going on here. This is a habited planet. This is a planet, a dynamic species lives on this planet. Right? You know that because otherwise, just no way you can light it up like that. Okay, so I'm very briefly then go through a couple of observations. How high will CO2 go? I think very high. And one of the things that follows is sea level. And sea level ought to be getting our attention, and it's not really getting our attention. So how high will sea level go? And this is important, I think. It's a good lesson in here because it embodies the notion of lags. Because we live on a water planet, what we do to the energy balance of the planet will always lag the response of the planet by roughly 1 generation, by about 50 years. So what our generation does I'm sorry, I keep hitting the microphone. What our generation does to the planet will not be fully reflected in the climate until our children, my children, are adults. And the same thing will happen to them. What they do to the planet will not be fully reflected in terms of the temperature and precipitation patterns, et cetera, until their children come along. And so this lag is, and it's a really fierce problem because we tend to be very short-term thought kind of creatures. It's not even close to a sentence, but you get my point. And that's, building that lag into the system is really troublesome. So my example of this is coal. This is, when you hear that coal has a 400-year lifetime, you hear that, I always hear this. We got lots of coal. Coal's going to last a long time. Well, I'm here to tell you that's a load, okay? This is what they're talking about. Coal has a 400-year lifetime. What they're saying is if we use coal at the rate that we're using it today, over 400 years, it will drop to nothing in the year 2400. If you just put 2% growth, which is what we're doing in terms of the economy of the globe, roughly, 1.8, something like that. If you put 2% growth on and you say that energy's got to grow to meet the needs of societies, which indeed is a very good prediction, given that most of the energy growth is going to be in the developing countries. With a 2% growth, note the scale. We went from 2,400, which is way over here, now to 2,100. That's just 2% growth. So very easily, we could take care of coal by the end of this century. And if you consider the fact that oil and natural gas are on their way out and will be so in the next 30 or 40 years, I just threw in 2% growth. Coal replaces oil in the year 25 to 2035 in terms of a primary energy source for electric cars or for gas, making liquids out of coal, whatever, not a boneheaded idea, but people have been talking about that. Anyway, the numbers just keep shrinking. So everything you want to throw on there is going to shrink the time. So I think it's very easy prediction based on two things. Number one, that with any kind of reasonable growth in society, we're going to burn all the coal. And number two, the fact that there's a generational lag in terms of response. And note that that's approaching one generation here. I think it's very, very likely we'll burn not only all the oil and natural gas, but we'll burn the coal. If we do that, we're talking about CO2 levels easily above 1,000 parts per million. So I'm thinking, 800 parts per million is a very conservative, low-level guesstimate for where we're going somewhere in the next 60, 70 years. And, 1,000 is not, thousands are not impossible. So as an example of the power of exponential growth, I won't tell you the full story about this. I'll tell you later if you want. But needless to say, I was bored and in a big meeting with a bunch of policy folks. And I calculated how much CO2 had been added to the atmosphere since 1997, which was when the Kyoto Protocol was ratified. And the answer really surprised me. 20% of all fossil fuels ever burned on the planet were burned since 1997. So 20% of all fossil fuels ever burned on the planet were burned since 1997. I calculated that from a CO2 standpoint. I asked a friend of mine who's in the energy industry to do the same calculation, and he very quickly, with publicly available data, gained exactly the same conclusion. That if you add up the oil, coal, and natural gas that have been burned, 20% of all that's ever been burned on the planet were burned since 1997. Okay, so it seems to me we're headed there, and we're going to change climate even if nothing else really happens on here. We're going there. So I think it's very important that we educate students about climate change. It's very important that we continue down this pathway because I don't think that the silver bullet's going to be coming anytime soon. Unless we get some political leaders who go way out of their comfort zone, which I don't think is going to happen. I think we're headed, for very large climate change. So what are some of the impacts? This is the slide I added. So there's some obvious impacts, and I'll talk about sea level because from a paleo-environmental perspective, when the planet warms, sea level rises. Those two things go hand in hand for two very simple reasons. One is if you warm the planet up, you warm the ocean up, and its volume expands. So there's a sea level rise from volume expansion. The other thing is that if there's any ice on the planet, then as you warm the planet up, the ice melts and the land ice will go into the ocean. Simple physics again. So a warmer planet has higher sea level, and a colder planet has lower sea level. And the wiggle room there is actually pretty impressive. Like you can have a climate that's pretty close to today and have sea level that's 20 feet higher. For us, this makes a huge difference. The planet could care less about 20 feet. But we, obviously, having built cities around coasts, really sweat 20 feet. But there's also, and you've talked about this, temperature, precipitation patterns change because the big circulation cells in the atmosphere begin to expand. And so where you have dry air sinking, like in Afghanistan, for example, moves north. There are very strong feedbacks in the system. Arctic carbon, we'll see permafrost melt. That'll add more carbon to the atmosphere. That's a very simple and easy prediction. If that doesn't happen, I would be stunned. The albedo will change as snow and ice melts. Will warm the planet up. If that doesn't happen, I'll be stunned. And there's some geopolitical feedbacks as well. We're already beginning to argue about what we're going to do in the Arctic. Shipping lanes are now opening up. Canada is finding itself needing an army way up north because there are already people impinging upon its territory. The Russians have dropped a flag at the North Pole. All sorts of things happen because areas of the planet that were heretofore not really accessible to us are becoming accessible to us. So there's geopolitical issues. One of my favorite geopolitical issues is this whole issue of geoengineering. That is, can we modify climate on purpose? And the answer is, of course we can, because we're modifying it on accident right now. Hell, if we actually did this with some kind of forethought, we could have a huge impact on climate. And so geoengineering is coming. But this is what's really important. Geoengineering to what climate? Who gets to choose the climate? This is a big, big question that not nobody, but only the policy wonks right now are thinking about. Because I'm pretty sure that Russia would choose a different climate than we would. And Canada would choose a different climate than we would. And the Pacific Island nations are going to choose a different climate than Russia might. So who gets to choose this? I'm pretty sure we're going to start putting mirrors in outer space. We're going to start putting reflective surfaces out on the ocean. We're going to start modifying our climate, our greenhouse gas behavior. We're already doing that. All of that's geoengineering. All that's going to change climate. And headed for what? And somebody's going to figure out that what is important and worth fighting over. And that's going to be a really interesting point in history. Yeah. So how high will sea level go? And you've probably seen this number. The latest IPCC report admits that they don't have all of the feedbacks in the system. And there are some very powerful feedbacks on ice sheets that mean that sea ice, that land ice will go into the ocean much faster than the IPCC projection. The IPCC projects in the neighborhood of 1/4 to 1/2 meter by 2100. The new estimates, which are out by the National Academy of Sciences, by other folks, is in the neighborhood of 1 meter by 2100. And I find that fascinating because we always do this. We pick a date, 2100, and then a number, as if, and you do it, I do it. You lock into this odd idea that, well, when it gets to 2100, it's 1 meter. It's going to stay there. It's never going to change again. And therefore, if we can, deal with 1 meter, we can deal with anything. But, of course, that's not what happens. It just keeps going up. And so how high is it going to go? And the answer are pretty interesting. And the impacts, I think, are eventually the sort of things that are going to get our attention from a climate change point of view, if we don't get our attention before then. These are, again, year 2100 projections, probably sooner than that. My guesstimate about coal burning tells me that this is more likely to be 2060, 2070, 2050, maybe even 2050 kind of thing if we really get serious about putting greenhouse gases in the atmosphere. But this is Miami with a 1 meter sea level rise. Miami's got some issues. And Miami, this was done by some really interesting folks at a lobbying organization called Clean Air, Cool Planet. They call me up every now and then and have me go up to the Hill in Washington and talk to senators and congressmen about this sort of thing. But they're a Washington-based lobbying group, and they did something really interesting. They had a bunch of us climate scientists go to places like Norfolk, Virginia, Miami, Philadelphia, other coastal cities. They focused on the East Coast at first, that have real problems with rising sea level. And they had to speak not only to the local politicians, the county folks, but they had to speak to the folks who build water treatment plants and who maintain water treatment plants and who maintain roads and other infrastructure. And what's fascinating was the folks who are down there where the rubber meets the road are already worried about this because sea level rise is already happening. They're already thinking about, if I have to site new water treatment plants, how far up the beach or how far up the mountainside do I need to go in order to make this thing function for the 70 to 80 years that we tend to have these things built for. And roads, and when I bury power lines, all these sorts of things. I went to Norfolk. One of the fine folks in Norfolk pointed out that they already in many neighborhoods, park their cars higher up, that is, out of their neighborhood, on nights with a full moon and a higher tide than normal. So they're already getting these strong high tides coming in, and they're already moving their cars out of harm's way because they don't want to get salt on the wheels. Anyway, Miami's got trouble. This is another question I get all the time is, why can't we build a dike? The Dutch did it. Well, there are places where you can seal things off, and you could contain sea level behind there. Fortunately, Venice is one of those, because Venice has got to be the best city on the planet. But you can't do that around Miami. I mean, we don't have the capability to build a dike all the way around southern Florida. So Miami's my poster child for sea level rise. Miami has no future. I hate to say that, but I think that is true. Okay, so how high will it go? It's not going to stop at 1 meter. Warming's not going to stop at 2100. What is our commitment sea level rise? That is, if we continue to do what we're doing, what's going to happen? I told you about this simple physics. When the Earth is warmer, you have less land ice and higher sea level. The Arctic warms much more than the rest of the Earth. There's what we call Arctic amplification that is primarily tied to the amount of snow and ice. When snow and ice melts back, you get roughly a 3 times increase in Arctic temperatures over the rest of the planet. So it's roughly a factor 3 increase. What does that do? If you look back at different sea levels in the past, this is now, I apologize, time now marches from today, going back in the past that way. Paleo folks mess with your time. During the last interglacial period, sea level was about 5 to 8 meters above present. The one before that, about 2 meters above present. You go back to the one before that, 3,000 years ago, about the same. About 400,000 years ago, about 20 meters above present. So sea level is a dynamic thing. The planet was a little bit warmer. You melt a little more of Greenland. And I have a picture of that. This is what we think the reconstruction of Greenland ice sheet looked like during the last interglacial period. Probably a lot of it melted off. Down on the southern end, that raised sea level by somewhere 2 to 5 meters of additional sea level. And 2 to 5 meters, I'll show you what that does to Miami here in a minute. You can put this on a nice graph. This is the sea level rise from Greenland versus temperature of the planet, and these are observations in the paleo record showing that here's the temperature of today, modern. If you just go back to the last interglacial period, this is our error bar around here. That's the interglacial period before that. And what you see here is an important feature is that as you start to warm the planet up, you start to melt the ice sheets off faster and faster. You can go to even larger. This is a figure produced by David Archer at University of Chicago, showing, again, global mean temperature and sea level. If you go back 40 million years ago, sea level was in the 60, 70 meters higher. Multiply these times 3, as you know. The Pliocene, which is I told you about last time, this is the last time there was 400 parts per million CO2 in the atmosphere. That was roughly 80 meters of sea level rise. This is the IPCC forecast for 2100 and the sea level rise that goes along with that. It doesn't even show up on the plot. That point's not exactly on this line. It's a half a meter up. And so you see that our understanding of the dynamic processes of feedback between sea level and climate change are not reflected in the models. They're not reflected in what you're hearing. If we left the planet alone and we increased the temperature by that much, then there's no reason we think that it wouldn't go up into this neighborhood. And this is an interesting neighborhood. 50 meters is a very interesting neighborhood. So how high is it going to go? At a minimum 10, 15 feet. I'm being very conservative. I think 20, 30, 40 feet by the time we're done here is certainly not possible. It's certainly possible. Many more meters, 25 meters or 80 feet would not be a surprise. So let me show you what, this is 2 meters, by the way. So Miami's, I think, toast at a meter, but because of infrastructure issues. But at 2 meters, it's really toast. This is what Florida looks like with 80 meters of sea level rise. And you can't even get maps of this. I had to go to Google. Fortunately, Google will do this for you. Let me put in 80 meters of sea level rise. What does that do to Florida? And basically, you're taking a state out.
Yellow's the water?
Yep, yellow's water.
Okay.
So, and I won't end with this, but I just would point out, Tallahassee makes it, by the way. But you got seafront property.
Yeah.
I noticed you're from Tallahassee. The other thing I would notice here, and this is my message to my students, what's very important that's located in this part of the world? Disney World. So obviously Disney is going to own Central Florida as an island. Out in the warm Caribbean, they're going to dock their big boats there. You know, the big winner is Disney, right? Ask yourself, follow the money, right? Who's the big winner? Who's causing climate change? I won't go there, but I'll let you. All right. Change is to be expected. That's what the past tells us. Sea level may be level, but it's certainly not constant. And we haven't begun to come to grips with that. And I think this is a really big, big problem in terms of money, in terms of our relationship with the planet, to have the planet change that much. Today's environment is no more normal than any other climate. And the big question, is it different when humans cause climate change? Because we're the only creature out there that can actually think about this. We're the only creature that can predict our impacts and modify our behavior according to those predictions. Not that we've done it yet. We're still behaving like every other species on the planet where we're trying to take over and dominate and dominate and dominate. It's a biological, ecological imperative that we seem to be locked into. But we're better than that. We're more capable than that. And will we actually get to the point where we exercise that mental capacity we have? I don't know. But if you folks aren't teaching the young ones, it ain't going to happen. I'll stop there.